this final session for today is on optics, in particular refraction. And I'm doing this because I can't remember who, one person that has agreed to come along really wanted optics. Refraction in particular is part of this course. So, and so we're going to do that. Does anybody have any questions on anything that we've done so far today? Because I will go through those first. If nobody does, then we will move straight on into the final session of today. So pop it in the chat if you've got anything. Right, now, I am going to start now with the refraction, the optics bit. And there's not much actual teaching that I want to do, but there is, well, one particular thing that I think it's worth talking about. Two things that I think it would be worth pulling up a whiteboard for. So I'm going to bring up a new whiteboard, and we are going to do refraction or optics. Okay. The first thing I want to talk to you about is Snell's law. And I think that you should use this version of Snell's law. N1 sine theta 1 is N2 sine theta 2. This is Snell's law, after a man called Snell. This law, the numbers in it refer to the material. So where N1 is the refractive index of material 1 compared to a vacuum. And N2 is the refractive index of material 2 compared to a vacuum. So we can write down N1 is equal to C over V1, and N2 is C over V2. Okay. And so if we've got, for example, a glass block, we've got a ray coming in right now. I'm going to draw my rays in red, and I'm going to use proper arrows because, oh goodness me, because it's really important. Oh, it's rubbish, isn't it? Come on. Let's get rid of the block a minute. Let's do it properly. No. Okay. Right, now the next thing I want to do is to remind you that all angles are measured between the ray and the normal. So I've just drawn in the normal. And so, right now, my rays, oh, look, it's dotted. I don't want it to be dotted. Let's make it solid, shall we? Okay, so my rays are going to be arrows, and I'm deliberately using, there we go. That's more like it. Okay, so sorry about the delay in getting that up and running. Right, so this is theta 1 because this is material 1. Okay, so it has refractive index N1. And this is material 2. And this is then theta 2 between the ray and the normal. Okay, and this has got refractive index N2. Okay, so this is really important. the material 1 is where the ray starts, material 2 is where the ray ends. Right, now, one of the things that gets you caught out is, at least on the, I think it's the AQA paper, you data sheet, you have an equation, sine C is equal to 1 over n. Now, that is a misleading equation, and I would prefer it if you never used it. This is true only if you start in the more dense medium, and only if the less dense medium is air. Okay, so this is true only if you start in the more dense medium and only if the less dense medium is air. So I don't want you to use that equation at all. I would much rather that you use this one. Okay, so how do you find the critical angle using the Snell's law equation that I prefer? So this is what you have to do. Okay, so let's make that slightly smaller. Okay, so I want you to start in the more dense medium. So, and normally when we're measuring critical angle, we do it with one of these semicircular blocks, a D-shaped block, don't we? Right, and we aim our ray at the middle of the back of the block, and we go through the block. Okay, so we end up going in like this all the way through. Oh, yeah. Better. Okay. Now, remember that the angle is measured between the ray and the normal. So if I draw in the normal, there it is. The angle of incidence, we've got to start inside the more dense medium. So that is theta 1. So this is material 1. And the only reason it doesn't deviate when it goes into material 1 is because it's going in along the radius of the circle. It's going in at 90 degrees. So right now, if theta 1 is the critical angle, then what happens is that my angle of refraction is 90. So there is my theta 2, and it's 90. So if theta 1 is equal to the critical angle, which we can call C, then theta 2 is equal to 90 degrees. So material 1 is the more dense medium, and material 2 is the air, the less dense medium. Okay, right now, if I now use that Snell's law at the top, I want to keep it on the screen so I can see it, right? I start with material 1, so this is N1 and this is N2. Can you see I go N1 is sine, and then theta 1 is my critical angle. C is equal to N2 and sine 90. And sine 90 is equal to 1, which is why this then reduces to the equation that I've crossed out. So I can get sine C is equal to N2 is the refractive index of air, which is 1. Sine 90 is 1, so it's 1 times 1, which is 1. divided by N1 is refractive index of my glass or block of whatever, right? So can you see this reduces to that, but only if this is air and you start in the more dense medium. Right now, you have to be in the more dense medium or you won't get total internal reflection. But this won't work. This one doesn't work if the second material isn't air. So what would happen if we put a layer of water on the back? Can you see now we've got a layer of water on the back. Now our second material isn't air. So the one, this N2, doesn't disappear. You can't, right, so let me draw in my normal. Make it dotted. And then solid. Okay, and then right now, where is material 1? Oh, it's still the glass. Where is material 2? Well, now it's my layer of water that's on the back of my block. Okay, so let's imagine that this is water. Water, the refractive index for water is about 1.3. Okay, the refractive index for glass, let's imagine this is glass, is about 1.42. Okay, so now if I now, whoops, say that this is my critical angle, this is my angle of refraction is 90, but I'm going to use the N1 sine theta 1 equals N2 sine theta 2. Can you see that I get N for my glass, this is material 1, is sine C equals N2 is the refractive index for water times sine 90. Okay, this is for my critical angle. So sine C then, can you see it's now NW is for water, it's 1.33 times sine 90 is still 1 divided by N for my glass is 1.42. But can you see it's no longer 1 over N? It's N for the water divided by N for the glass. This equation, the sine C is 1 over N, does not apply because the 1 requires that you've got air as your second material. And here we do not have air as my second material. Okay, so that's the first thing that I really wanted to go through with you is this, this version of Snell's law. Okay, right now, the other thing that I want to do, to go through with you is that really, I mean, it's really just a statement that you've got to remember your triangle rules. It's all about geometry. Okay, so most optics questions are about geometry. So when it says to show something, just remember that the angles in a triangle add up to 180. Okay, remember the angles in a triangle add to 180 degrees. Okay, so right now, that is it as far as the teaching is concerned. Okay, so what we're gonna do now is we are going to stop with that and going to pull up some questions. So let me share my screen with you. Right, my potential divider questions are over. So, and I'm going to go to optics. And I've got refraction at plane surface A and B. Let's go with B. I'm opening up this one. Right, now this is an optical fiber. The optical fibers used to feature heavily. They feature less heavily now. This is a pretty typical question. I go back and do that one, or that one, or that one. I think I'm going to start with this one. Okay. So we have quite a lot of information, don't we, about what's going on here. So, but we are going to do our ninja question reading. So the topic of this question, what is the topic, please, people? Pop it in the chat. Yeah, optics. I've written refraction. So yeah, so optics, refraction, optics. Yeah, that's good. Right, so the equations. So equations we need to write down. Okay, from the data sheet, we've got Snell's law, n1 sine theta 1 equals n2 sine theta 2, and we've got n is equal to c over v. Do we need anything else? I don't think we do. I'm going to leave it like that. If we need another equation, then maybe we'll come to it. So we've done the equations. So number 3, how many marks for the first part? 1. Yeah, just a 1. 1 mark. So it should be straightforward, this first bit. Then next bit, what is the command word? What is the command word? Yeah, it's confirmed, but it's confirmed by calculation. So basically it's calculate, isn't it? Yeah, I think it's calculate, really. I mean, confirm, but yeah, calculate. It's a calculate. Okay, so I'm going to write calculate down. Okay, calculate. Right, and then the next thing that we're going to do is we are going to highlight any numbers. So what numbers do we have? We have 15 degrees, we have 10 degrees, we have 45 degrees, we have 90 degrees. We have 1.49. Okay, do we have any other numbers? Well, there's a number down here, but that's not the same question. Okay, right. So we've highlighted all the numbers. Right now, what we need to do is highlight any words that mean numbers. Are there any? I don't think so. I can't see any. Right. So then the next thing is we're going to read for meaning, and we're going to add to our diagram because there's already a diagram if we need to. So we've got a ray of light and it passes from air into a glass prism. So there is the ray. Okay, that's fairly straightforward. And it's going into the glass prism and it's bending. And it says, confirm by calculation that the refractive index of the glass is 1.49. So I think that's fairly straightforward. Okay, I haven't needed to add anything to the diagram, I don't think. I think it's fairly straightforward. Okay, so which equation then are we going to use for this calculation question? Can you pop into the chat which equation we're going to use? There's only 2. Yep, we're going to use the n1 sine theta 1, etc. Right, so we're going to use that. Right, so let's do it. So we write down n1 sine theta 1 equals n2 sine theta 2. So I'm going to call this material 1 and this material 2. And my Snell's law, I am going to apply to that refraction, the one with the green ring around it. Okay, that's the refraction I'm interested in. So material 1 is air, so that is 1. And but what I'm trying to do is I'm trying to confirm the refractive index of material 2. So before I go ahead and put my numbers in, I'm going to rearrange my equation so that I've got it in the form N2 is equal to. So it's N1 sine theta 1 over sine theta 2. And now I'm going to plug my numbers in. N1 is refractive index of material 1, which is 1, times the sine theta 1 is a sine of 15, divided by sine theta 2 is sine of 10. Right, now, I want you please to check that your calculator is in degrees. Hopefully your eyes are better than mine and you'll be able to see it easily. So, and I've got sine of 15 divided by sine of 10. And I end up with 1.49. Okay, so can you see, I'm right now, I need to put in an extra significant figure more than they've given us, because this is basically a show that, isn't it? So I'm going to put not just 1.49, but 1.49047, right? And I'm then going to write down it's approximately equal to 1.49. So now I have shown or confirmed by calculation that my refractive index, but because it's a show that, and because they've given you the answer, you need these extra significant figures for a show that. I know it isn't a show that, it's a confirmed by calculation, but it's like they've given you the answer, haven't they? Right. So that's the first bit. Right, now the next bit then, it says on figure 1, draw the continuation of the path of the ray of light until it emerges back into the air. It says write on figure 1 the values of the angles between the ray and any normals you have drawn. Okay, right, so I am going to get rid of everything so that my diagram is nice and clean. And but I just want to point out that they have made you figure out that the refractive index is 1.49. This is, it's kind of like a signpost question. They've given it to you because you will need it. You will need it. If this is my refractive index, then when this, because I've got to draw how this is going to go, right, is that, there's my normal, is that bigger than the critical angle or not? Because if it's bigger than the critical angle, then this is going to happen. If it's smaller than the critical angle, then this is going to happen. So you've got to decide, is it going to totally internally reflect or not? Right? And they've told you that the critical angle is less than 45 degrees. Okay, so what are we going to do now then? Right, so let's clear all my drawings a minute. My critical angle is less than 45 degrees. Right, now I'm going to go for a very thin line and I'm going to make it red and I'm going to extend this ray until it hits here. Right, now, if I now put in my my normal, which I'm going to put in black, I need to figure out whether this angle, I'm going to call it theta, is bigger than 45. If theta, let's make it possible to read, shall we? If theta is greater than 45, then I'm going to get total internal reflection. How can I figure it out? Right, now, and this is what I was meaning in the last bit on my whiteboard where I said you have to use the angles in triangles. So this is a prism. The grey triangle is a prism. we've got 45 degrees here, 90 degrees here. So what is this angle? I'm going to call it alpha. Tell me what alpha is. Hugo's way ahead. Yeah, it's 45 degrees because the angles in right angle, well, in any triangle add up to 180. So that one's 45. Okay, that one's 45. What is, I'm going to do it in green so you can see it easily. What is the green angle? Come on, guys, what's the green angle? Remember that the normal is always at 90 degrees to the surface. Yeah, the green angle, this angle is 100. So if we've got 100 as one of our angles and 45 as another one of our angles, what's the blue angle got to be? And you see this needs to be 180 minus 100 minus 45, which gives us 35 degrees. So if the blue angle is 35, what then is theta? Yeah, so theta is 90 minus 35. So we can, right, can you see it's just angles in triangles, really? So we can get what theta is, right? So we now know that theta is 55 degrees. Right now, we've been told, because it tells us that the critical angle is less than 45. So what is going to happen to the ray? Is it going to totally internally reflect or is it going to refract? Yeah, it's going to totally internally reflect, isn't it? So I can now draw in right now. And the next thing you've got to do is you've got to make sure that it looks the same, both sides. So this angle I'm going to draw in, this one is also theta. That's got to look the same size. Right now, which means that, oh, look, that is going to be 35. That's 45. Oh my goodness. So can you see the symmetry of this? This is going to come out of there at 15 degrees. Can you see the symmetry? So just because that angle's also 100, well, I have to do it in green, shouldn't I? Let's do it in green. That one's 100. Yeah? Those two triangles with all the coloured angles in, they're similar. They have to be. Okay. So right now it says, write on figure 1 the values of the angles between the ray and any normals you have drawn. So I've drawn in one normal. In fact, I've drawn in two, haven't I? Because I did a red dotted one as well. So I would need to write in there 55. I would need to write in there 55. I would need to write in there 15. And what is that one? That one is 10. Can you see? And you have to carry it on until it emerges back into the air. So you have to draw all of it. Okay? Right, so I really ought to make that red one a bit thinner and straight. Like that. Okay, so now now I've drawn in all of the angles to all of the normals, and I've followed it, the path of the ray, until it emerges back into the air, and I've figured out whether or not it's going to totally internally reflect. The only other thing that I really should do is add to my arrows, sorry, my rays, single arrow for each ray, a single arrow for each ray. And I am going to insist that you use a ruler and a sharp pencil. And it is really crucial that you are accurate when you do this. So you will need a protractor. Now, obviously, you can't use a protractor on a computer screen, but you absolutely can and should, in fact, must, when you're doing questions like this in the real exam. So make sure, I mean, it's not big bucks. You need a 30 centimetre ruler, which will set you back about 60p. A regular school protractor, which is probably about 40p. Okay, but you need both of these, and a sharp pencil, preferably a pencil that can't go blunt. So you want one of those ones where you press the button and you get a thin lead comes out. So it's always sharp. You can't have a blunt one. Right now, right. So that is part B. Does this question carry on? So let's clear all my drawings and move on. Oh, it carries on. Aha, right. So now we've got a second prism. So now our critical angle has changed because prism 2 is not air. So we have to bear in mind that the critical angle might change. Okay, so now it says, let's do our ninja question reading. We've got this different refractive index, right? So I'm going to let's start again. So with on our right, so it's the topic is still refraction, right? And the equations are still the same. And this one. And the third thing is how many marks? Well, we've got 7, which we've got to split into 3. So it's 2 or 3, 2 or 3, 2 or 3, probably. Yeah. So we've got 2 or 3 marks. Right. Number 4. What is the command word for C part I? Pop it in the chat. Yep, there it is. Calculate. Okay. So it's calculate. Calculate. Okay. And then the next thing that we're going to do is we're going to highlight any numbers. How many numbers? We've got a second prism, prism 2, as well as prism 1. Okay, we've got a refractive index of 1.37, and it's firmly, so there's no gap, there's no air in between the two. That word firmly, it's kind of like a word that says there's no gap, there's no gap. Right, it says the ray strikes the boundary between the prisms. Calculate the angle of refraction of the ray in prism 2. Okay, so I've been reading for meaning. I've got numbers still here. This is still 45. It's not written in, but I'm now going to add it in. That one's 45. That one's 45. That one's 45. That one's 45. That one's 90. It's a second prism. And right, I think that now I've read for meaning. All I've got to do is to calculate the angle of refraction of the ray in prism 2. So I'm going to now draw in my continuation of this. And this has got a lower refractive index than this one, which means it will bend away from the normal. So it's going to bend something like that. And I need to put in my normal. Let's make the normal a different color. So there is my normal. And now what I'm going to do is I'm going to label the angles. So this then is theta 1 and this is theta 2. And we are going to apply our equation to this refraction. Okay, not the first one, the second one. Okay, right now, we do know, however, that theta 1 is 55 degrees because we already worked it out on the previous page. So theta 1 is 55. So now, which equation are we going to use to calculate the angle of refraction? We've only got two equations. Which one are we going to use? Yep, we're going to use Snell's law. Okay, so we're going to do n1 sine theta 1 equals n2 sine theta 2. So this is theta 1 because this is, this is material 1. So that's where theta 1 is, and this is material 2. Okay, so N1 is in material 1. And what do we want? We want the angle of refraction in material 2. So we want theta 2. So I'm going to do sine theta 2 on its own. Let's get rid of the, move it all over. So sine theta 1 over N2, right? And now I actually want theta 2. So theta 2 is equal to sine to the minus 1 of n1 over n2 times sine theta 1. And now I can do it all in one step. Can you see? There's my equation. There's my rearrangement. There's another rearrangement. So now theta 2 is the angle that I actually want. So it's sine to the minus 1 of, right, n1 is the refractive index of material 1, which we worked out on the previous page was 1.49. n2 is the refractive index of material 2, and we've highlighted it. Oops. And I don't know what it's doing. It's messing me about. Right, so 49. Right, N2 is the refractive index of material 2, which is 1.37. And we're going to multiply that by sine of, and it's theta 1, which is 55 degrees from our previous page. Okay, now if I make my sum look like that on my calculator, so if I do shift and then sine, and I've got an open brackets, and then I put in my fraction, and then I do 1.49, and then I move down, and I do 1.37, and then I move across, and then I do times, and I do sine, and I do 55, and I close my brackets, and then I close my brackets again, and then press equals, and I get, it's all in one go, 62.99 degrees, which is approximately 63 degrees. Can you see what I've done to try and make it as clear as possible? Now, obviously, there's not that much room in here, but can you see the process? Can you see that it's all about triangles? Can you see that we're using the previous stuff? Okay, now we're being told to calculate, there's the command word, the speed of light in prism 2. Which equation are we going to use for this calculation? Yep, N is equal to C over V. We want V, so we're just going to rearrange it. So this is the speed of light in material 2, so we want a refractive index for material 2. So this is 3 times 10 to the 8 over, and the refractive index for material 2 is up there, 1.37. So the speed of light material 2 is 3 times 10 to the 8 divided by 1.37. Right, if you get a number, so this is 2.19 times 10 to the 8 meters per second. If you get a number that's bigger than 3 times 10 to the 8, you know that you've gone wrong. You've got it the wrong way up. You've multiplied instead of divided, perhaps, something like that. So you should check for sense when you're doing refractive index questions about the speed of light, because it's very easy to think, oh, well, it's going to go faster. Yeah, you can't go faster than 3 times 10 to the 8, okay? Right, then it says, draw a path the ray could follow to emerge from prism 2. Okay, so this angle should be 63. Again, you really need to measure it and check that it really is about right. I mean, I don't know if that is. I'm going to put my protractor actually on the screen and see whether or not it's 62. Yeah, I've got it about 65 actually. That's not bad. Okay, so you want to make it approximately the size that you should have had, right? Can you see? I hope you can see that this ray is it's going to. Sorry, I'm trying to find the red. And this needs to be the fine line. Can you see that this ray is going to bend away from the normal when it comes out? But it's really clear that it's approaching the air prism 2 boundary at much less than 45 degrees. So and so it's unlikely to totally internally reflect at that point. So I'm going to put in the normal. Oh, that's rubbish. Let's try that again. Put it in the right place. That's more like it. Okay, so my angle of incidence, can you see there is really small. So it's not going to totally internally reflect, which means then that's my angle of refraction. And but it's the symmetry is no longer there because we've gone to a different refractive index material. Okay. Okay, so that is drawing the path the ray could follow from prism 2 into the air. Can you see you've got to actually go into the air? Okay, does anybody have any questions about this? Can you see that it's geometry, it's angles and triangles, it's using the Snell's law, the being really critically clear about which is material 1, which is material 2, and then you don't get confused. I hope that this is clear. Has anybody got any questions? No questions. No questions. Brilliant. Right, so let's do another one, shall we? That one, that one, that one. I don't know. What should we do? We've done a triangle one. Let's do this one. This one's a weird shape. So let's have a go at this one. Okay. The figure below shows a ray of light passing from air into glass at the top face of glass block 1 and emerging along the bottom face of glass block 2. The refractive index of glass block 1 is 1.45. Okay, so we are going to do this question and we are going to figure out what the topic is. Well, the topic is refraction. And then the next thing we're going to do is look up the equations. And then the next thing we're going to do is we're going to figure out what's the number of marks. Okay, so number of marks. If I scroll. There's 3 parts to A and there's 7 altogether. Judging from how many lines, it looks like it might be 2, 2, 3, perhaps. So probably 2 marks. Probably. Okay. And then having got the number of marks, now what's the next thing we've got to do? We've got to figure out the command word. What's the command word for this first question? Yeah, calculate. Really straightforward, this question, isn't it, so far? Okay, the next thing we're going to do is we are going to pull up all the numbers. So let's make that a bit fatter. So numbers, over, isn't it? So 1.45, we've got 15, we've got 51.3, we've got 37, 8.7. What else have we got? This is material 1, this is material 2. I think that's all my numbers. Right, any words that mean numbers. The figure below shows a ray of light passing from air into the glass block 1, emerging from the bottom face of glass block 2. Right, it says calculate the incident angle theta 1. So calculate the incident angle theta 1. So if we're going to calculate the incident angle theta 1, then we're dealing with this refraction. Okay? What equation could we use? Which of the equations that we've got would we use for calculating theta 1? Yeah, so we're going to use Snell's law. So it's n1 sine theta 1 equals n2 sine theta 2. So in fact, this is material 1 and this is material 2, despite the fact, confusingly, it's got glass block 1. Okay, the refractive index of glass block 1 is n. I'm going to put what am I going to do? I'm going to call that N2 and I'm going to call this N3. N1 is equal to 1. So N2 is equal to 1.45. Okay? And what I want is theta 1. So I'm going to now use this equation and I'm going to rearrange it. So I've got sine theta 1 is equal to N2 over N1 sine theta 2. And then I'm going to say theta 1 is equal to sine to the minus 1 of N2 over N1 sine theta 2. And I can do sine to the minus 1 of N2 is 1.45 over N1 is 1 times sine theta 2, sine of 15.5 degrees. Make sure your calculator's in degrees. What is theta 1? So shift sine to minus 1. 1.45. Now I get theta 1 is 22.8 degrees. Okay, so we've done this first one, and we now know that this is 22.8 degrees. Okay, right, having done that, what's the next question? It says, calculate the refractive index of glass block 2. The refractive index of glass block 2. Right, I'm going to change colour. What equation could we use to measure the refractive, or calculate the refractive index of this one? The same equation, yeah, okay, I agree. So we're going to use the same equation, n1 sine theta 1 equals n2 sine theta 2. Right, now, are we going to use the refraction at A, or are we going to use the refraction at the edge of the block? Let me do that one in a different colour. So are we going to use the blue refraction or the purple refraction? Purple. Why do you say purple? We know that the refractive index of air is 1, yeah. So can you see? I mean, I think you're right. I mean, we could do it from the middle, the refraction at A. We could do it because we could find out what theta 3 is, probably. Maybe. No, I'm not sure we can. Ooh. Yeah, no, I don't think we can because we don't know what this angle is or this angle is, do we? We don't have that information. So I think we have to use the purple. So we're going to do the purple refraction. So we are starting in this now is material 1 and this is material 2 for the purple refraction. So our refractive index in material 1 is actually N3, there it is, and that's what we're trying to find. So N3, okay, times sine theta 1 is 38.7. So this is my critical angle, in fact, is equal to N2, well, this is 1, because it's the refractive index of air, times sine 90. Oh, look, that's 1 equals 1. So can you see that I can work out what my refractive index is, N3, because it's 1 over sine 38.7 degrees. So let's shove that in there then. So 1 divided by sine 38.7. And I end up with N3 as 1.599, which is approximately equal to 1.60. So this has got a refractive index of 1.60. Okay, so that's the second part of that one. Right, so let's just quickly scoot down and see what the third bit is. It says, what's the angle theta 3 by considering the refraction at point A? So now what we've got to do is we've got to do refraction in the middle, the blue one. Okay, so we've got to, let me clear out all this stuff on the right hand side. So we're now going to do blue refraction and we've got to find theta 3. So this now is material 1 and this now is material 2 for the blue refraction. Okay, because we start in the glass block on the right and we end up in the glass block on the left. Okay, so N1 is for the right and N2 is for the left. Okay, now I want theta 3. So can you see theta 3 is my angle in my material 1. So I'm going to write sine theta 3 is equal to N2 refractive index 2. That's this one. So that's the purple one. So that's actually 1.60. Sine theta 2 is 51.3 divided by N1. This is this one. 1.45. Can you see how easy it is to get confused? Okay, so theta 3 then is equal to sine to the minus 1 of 0.6 times sine 51.3 divided by 1.45 gives us theta 3. 1.6 times sine 51.3 1.5 I get theta 3 is equal to 59.4 degrees. Okay. Does this all make sense? I hope it does. I hope that this has cleared up quite a lot about refraction. Basically, it's just about angles. Even when it's show that, just do the geometry. Just say this angle and label the angles A, B, C, D, and say angle A is this. So angles in a triangle, which means angle B is this, and da, da, da. So just even if it's a show that, just do it the same way you would do geometry question in maths. Okay, so hopefully that has solved your problems in refraction questions in optics. Right.